today's lesson is going to be about how people first started to get the rules of chemistry. So the rules of chemistry that people were just about getting to grips with in the 1700s. So going back in history a little bit here. And these are the sorts of things that we teach you guys in like your first year at secondary school. And we just say, oh yeah, this is how chemistry works. But obviously somebody had to invent this stuff. Somebody had to figure this stuff out. And it took more brains than you and more brains than me to figure some of these rules out. Even though I teach about it these days. So I've got a question for you. When you burn, like set light to some stuff, like a bonfire or a barbecue, charcoal, at the end, if you weigh all the ashes that are left over at the end, it weighs less than the charcoal fuel that you had at the beginning. So who can give me an idea of why? Like, why do you think it weighs less afterwards? Where do you think that extra weight has gone? So let's give you an example here. So if I put 16 grams of charcoal and set light to it, then after the fire is finished and after the flames have all died down, then at the end of it, weighs only 12 grams. So where is that extra 4 grams of, it's called mass when you measure something in grams, where's that extra 4 grams of mass disappeared off to? Jesse, that's a good idea, smoke. So we know that when you make a fire, it's not just flames, but loads of smoke, and sometimes particles comes up into the air. So that 4 grams could have gone into the air. Alfie, because the weight of the oxygen. Oxygen is important to this lesson, and that's right. So oxygen has got something to do with it. So, like, are you saying that there's oxygen in the fire, and like Jesse's saying, it goes up in the smoke, so it like disappears upwards, and that's gone once the fire is finished? You're on the right lines, guys. Actually, that's good. So. That is very off topic, Jesse, but keep us informed. Probably, Alfie, evaporation's the wrong word to use there, because evaporation is when you have a liquid, and the liquid is heated up to turn into a gas. So there's no liquids here exactly. This is what we call a combustion reaction, like a burning reaction. Emily says maybe it's sort of disintegrated. So disintegrated is a weird word to use. It kind of means breaking apart or breaking up. So yeah, certainly the charcoal's breaking up, I suppose. And fires do have something to do with energy, but energy, like heat energy and light energy, they don't weigh. It's difficult to weigh them in actual grams, Lucy. So it's not so simple to just say, oh, there's 10 grams of heat energy or 10 grams of light energy. So you got some good ideas there, guys. So I'm going to try and answer this question, like what happens, why the charcoal weighs less after we've finished, and we're going to try and do it today. So in the 1700s, so 300 years ago, scientists were called alchemists, and their main plan was they liked to try and they were trying to change things into gold. That was the key thing that alchemists were after. But also they loved setting things on fire, and they had an idea called the fire theory. And their theory was that when you burn something, chemicals had fire inside it. And it does. So I was looking for a cartoon of an alchemist, Jesse. So this is what I came up with. But basically, their theory was whenever you set something on fire, it had fire inside it, and basically the fire got released up into the air. And because it didn't have any fire anymore, what you had at the end weighed less. Okay, so that was called the fire theory. Whenever you burn something, whatever fire is inside, it goes up into the air. And people saw flames coming out, so that kind of made sense, and it weighed less afterwards. All right, so that was called the fire theory. A lot of people believed in the fire theory. It had a bit of a problem, though. And I'll show you the problem. So it came to do with some chemicals. And an example here, this alchemist is trying to make the chemical phosphorus. If you've never heard of phosphorus, It's number 15 on the periodic table, and it looks like this. Can you see this? It's this white stuff, white crumbly stuff here. It's called white phosphorus. It is really poisonous. A lot of scientists probably died or killed themselves working with phosphorus. It sets fire really easily. It sets fire so easily that if you just put it on the table in air, it sets itself alight. So you have to keep it underwater to stop itself from setting fire. But the big problem was that phosphorus actually gets heavier when you burn it. Okay, so it makes flames, makes light, and then it gets heavier. And if you were paying attention to the fire theory, that is totally against everything they thought about the fire theory. They thought the fire escaped and it got lighter. So what was going on with phosphorus? Why did it get heavier? This was a big problem. So I found a little video here of somebody setting light to phosphorus. We are not allowed to do this in the science lab because phosphorus is super dangerous, toxic, flammable. You can do this with, if you ever set light to magnesium, you know, the sort of like sparkly metal, I'm sure you've done that in class before, set light to magnesium. It does also get heavier in the same way. Jesse wants to get hold of some phosphorus anyway. Right, I'll check the rules on phosphorus, Jesse, see if we can order some for next time we reopen the school, we'll get some phosphorus. It's very reactive, Alfie. It does set itself on fire, but the key question is, how come it gets heavier when everything else is supposed to get lighter? It's going against the fire theory. So, I'll show you this little clip here. I've got to mute myself when the video's playing, so I'll be back in a second. It's only a couple of minutes long. Oops.
And you can see that the phosphorus is oxidised in the air, and it's taken some of the paper with it to generate a nice P for phosphorus. So this is a sample of my favourite element. This is phosphorus. Phosphorus is a very, very reactive element, especially this type of phosphorus, which is white phosphorus. Phosphorus itself, elemental phosphorus, exists as a number of different allotropes, so a bit like carbon with diamond and graphite. And here we have one of those allotropes. It's white phosphorus. It exists as discrete molecules of 4 phosphorus atoms connected like a pyramid. And those 4 phosphorus atoms are really strained and really reactive, and they want to really react with oxygen as quick as they can.
This is the sort that is used in phosphorus bombs. It burns very easily and gives a very intense white light out of it.
So instantaneously you can see that fantastic oxidation reaction as the phosphorus reacts with the molecular oxygen in the vapor, in the gas inside the flask.
Though you can put it out quite easily by putting water on it, provided that it hasn't got too hot and the water will just evaporate.
Very reactive form. The other
Alright, so you just saw phosphorus being set on fire, and I think the word phosphorus was mentioned about 20 times in that video, as it should be. But here we go, you can see that as soon as they're just poking a piece of hot metal onto it to get the reaction started a bit more quickly, but it is already, it will just, you just put a tiny piece of phosphorus onto the sand here, so it's sand in a glass flask, put a piece of hot metal there, and even without the hot metal it will set itself alight there. And it glows very brightly. That's why it's so dangerous. That's just a tiny piece of phosphorus. He mentioned there that phosphorus is used as a weapon. Phosphorus bombs are a really horrible weapon to drop on people. Incendiary bombs. They burn anything that they can touch. Anyway, so that's gives you an idea of what phosphorus looks like. It has to be kept underwater, like I said, so it doesn't set fire just on its own. But how come it got heavier? So that's the key thing. So let me just recap what we've done so far. So we've looked at 2 burning reactions. They're called combustion reactions. You burn some charcoal and it weighs less. You burn some phosphorus and it weighs more. One goes from 16 grams to 12, one goes from 10 grams up to 11. There's something a bit weird going on. The fire theory says charcoal loses its fire and it weighs less afterwards, but the fire theory doesn't really explain why phosphorus weighs even more afterwards. Okay? No, I don't think that explains it yet, Jesse. So Right, it takes a little bit of a hero, a science hero, to try and explain some of this stuff here. So remember, this is in the 1700s here. So my hero for today, I'll mention a few like excellent scientists as we go. And my hero for today is a Frenchman called Antoine Lavoisier, and he was born in 1743. Here he is. This is a picture of him. Now, I mentioned his wife a little bit in today's lesson because he was, unlike a lot of old dudes who became scientists later on in life, Antoine Lavoisier was rich, had a lot of money, and partly because his wife's dad was rich and owned a family business, and he married his, but that's probably not why he married his wife. Or maybe that was part of it, I don't know. But anyway, he was rich, had a lot of money, and had a lot of time on his hands because his job didn't take that much time. So he could spend a lot of time in his own personal laboratory. So here he is, age 28, writing some scientific papers. Here's some of his scientific experiments. See this little glass, hollow ball of glass balloon that's called. A gold digger. That's right. So he was a gold digger. Marie here, her dad was pretty loaded. So, so here he is writing some experiments here. No. His wife was definitely not using him for his money because he didn't have any money. His wife was from the rich family, so it was the other way around, really, Alfie. So basically, in the previous lesson, we learned about an Englishman who discovered oxygen gas, Joseph Priestley, and he discovered it by trying to keep mice alive in a jar. And he found that plants made oxygen gas and could keep the mice alive. Without oxygen gas, the mice would suffocate. So he just learned about Joseph Priestley's experiments, and he found out about this oxygen gas stuff. Now, previously, before the discovery of oxygen gas, people thought that air was just air, and maybe it just came in different forms, but they didn't realise that air was a mixture of different gases. So I've just got another little clip here which introduces Antoine Lavoisier and just mentions his wife Marie as well. So just remember this little picture here. Let's watch a little bit of this. Here he is. Very handsome looking dude.
Born into a well-to-do Parisian family, Lavoisier had received a fine education and taken a degree in law. Now 28, he had joined a consortium that collected taxes for King Louis XV.
As a result, Lavoisier became a very wealthy man.
But his true passion was chemistry. Lavoisier spent 3 hours in his private laboratory before work every day and returned there after dinner, often accompanied by his young wife. Marie-Anne Paltz was the daughter of one of Lavoisier's business partners.
Antoine?
Oui?
She was just 13 when they were married, but bright, outgoing, and mature beyond her years.
Lequel est-ce que tu préfères?
Marie-Anne was virtually his collaborator. She knew English, learned chemistry, assisted Lavoisier in the laboratory. She was an extraordinary person. Had she lived in our own time, she probably would have become an outstanding scientist in her own right.
One of Marie-Anne's most important roles was to create the diagrams and illustrations that accompanied her husband's published work.
Marie Lavoisier's drawings give us the eyes to look directly into Lavoisier's laboratory. We can see the people, we can see the devices, we can see the arrangements of those devices. We can understand what Lavoisier did so much better because of what Marie drew.
Spurred on by Trudaine.
All right, so that was a little introduction to Antoine Lavoisier and his wife, who was only, and this is a bit shocking in today's times, only 13 at the time when they got together, when they married. But she was smart, learned English, learned science, and she was assisting him in many of his experiments. And probably if she was around today, she would have been like a really great scientist herself. So the mask outfit was when they were, so oxygen had just been discovered, like I said, and they were doing experiments with this. They thought it was like an improved gas. They thought it improved your performance when you were breathing in pure oxygen. and that man was in there wearing the mask because they were sending oxygen into this mask, and then making him do exercise. They saw him stamping his feet, pushing on a pedal, and then measuring his blood pressure, measuring his heart rate, and so on. So they were trying to do a little bit of experiments with oxygen. Antoine Lavoisier was like really interested in finding out a little bit more about this gas because it had only just been discovered. So now, what did he do with this oxygen? So basically, this comes down to one of the things that Lavoisier was most famous for is that he managed to weigh gases for the first time. Now, when I talk about this in class, a lot of people say, hang on, you can't weigh a gas. Gas is just, it's just the air. It doesn't weigh anything. Is anyone going to admit to thinking that once upon a time, that air does not weigh anything? Air is weightless. Can you weigh a gas? This glass balloon here is in every painting of Lavoisier that you can find. So Antoine Lavoisier, his wife Marie, and this glassware here is one of the things that he was most famous for, this glass balloon. He used it to weigh gases. If you go back to the previous picture, what do you see if I get my head out of the way? Down here, glass balloon for weighing gases. So, no, air isn't weightless, Jesse. So, I did a little bit of digging around and I found my old university chemistry teacher. He's here. This guy, when I was at university, was giving me lectures, and he doesn't look much older than he did when I was at university. So I look a lot older, but he doesn't. But here he is. He's just demonstrating how much air actually weighs. So it's just a minute long. This is the last video clip. But the memories, Lucy, that's right. Memories of university. I'm going into the chemistry lab. He was actually one of the, you get good lecturers and you get bad lecturers at university. And he was one of the excellent ones. So he's showing you how much air actually weighs. So if you ever thought that air doesn't weigh anything, he's going to prove you different. So let's have a look.
I'm going to take all of the air out of this flask here. So at the moment, it's full of air. I'm going to use this special pump here to take the air out. So there we are, evacuating, taking the air out of the flask. And we're going to, we'll weigh the flask first of all. So we'll just set this to 0 on the scales here. So 0.00 grams. Now I'm going to open the tap and we'll see how much the air weighs inside here. Now the air is rushing in, you might be able to hear it. And the scales now say about 2.5 grams. So there's 2.5 grams of air inside this flask. Well, okay, let's see how much 2.5 grams weighs. I've got a little jelly baby here. Let's just see how much he weighs. Well, the whole jelly baby, there he is. He weighs about just over 5. Well, let's just rip off his head, perhaps. There we are. Oh, his legs are just about 3 grams. So it's about a headless jelly baby. Okay. Now that doesn't sound very much, but just think how much air we have in the lecture theatre here. If we put all of this and we managed to weigh all of the air here, that would come up to about the same as a small elephant just in here, just the air pushing down. Well.
So, maybe that he decapitated a jelly baby. That's right, Jesse. But he did it for the benefit of science. So let's just rewind it a little bit. So the first thing he did there was he suctioned the air. It's called a vacuum pump. Suctioned the air out of this glass balloon, which means that you had a vacuum inside, a place where there's no air particles. So you put an empty glass balloon on the scales and set it to 0, so no air in there, and then he opened a little tap at the top to let the air rush inwards, and it weighed 2.5 grams more. So that tells you that the weight of the air inside that glass balloon was 2.5 grams. And just as a comparison, he gave you half a jelly baby, which is about 3 grams there. So air does weigh something. And then he was just saying, well, what about in that large room there, the lecture theatre that he was talking about? If you took all the air in that, then it would weigh, you know, an elephant's worth. So it would weigh an awful lot. So the weight in the room in your house right now is probably, I don't know, a few kilograms of air. So air does weigh something. And this is really important to what Lavoisier discovered and what he discovered next and how he became famous. So this is the most difficult bit of science in today's lesson. I've tried to make it as simple as I can. So if you imagine, so just think back to the phosphorus that they set on fire, and we're trying to decide why phosphorus got heavier. And so I've drawn a little box with some phosphorus in it. That's the P. So phosphorus is P on the periodic table. Here's some phosphorus. And what Lavoisier could do, because he had discovered how to weigh gases with his glass balloon, he could weigh the oxygen gas, or weigh out some oxygen gas. Remember, this has only just been discovered in England like 2 or 3 years ago. So it was really new science, how to weigh gases. So he weighed the phosphorus, it weighed 10 grams. He weighed the oxygen gas that he had to react with the phosphorus, and it weighed 4 grams. So anyone say in chat how much does one atom of oxygen gas weigh? Hello Tom, nice to see you. Don't worry, you'll be able to catch up if you like. If you watch a bit of the video later, all this video will be up on the channel later. So Josh, that's right. So if we just say 4 grams for 4 atoms of oxygen, so each one of these must be 1 gram here. All right. So then after burning. And Daisy's here. I'm not sure which Daisy it is though, so good afternoon Daisy, nice to see you. So then he set light to his phosphorus, made that massive flames, and afterwards, this is what changed. He found that the phosphorus had gone up to 11 grams, but, okay, so people knew that already, phosphorus got heavier, but this is what Lavoisier discovered, that the oxygen gas had got lighter, had gone down to 3 grams. Daisy Fryer, nice to see you. So he's just discovered something here. By measuring the weight of the oxygen gas, he's sort of explaining why the phosphorus is getting heavier. And he came up with the idea that the oxygen gas, or at least some of the oxygen gas, was going on to join up with the phosphorus, and this, nobody had ever thought this before. Nobody had just worked this out, because remember, oxygen was only just recently invented. So when you burn phosphorus, oxygen from the air, some of the oxygen goes and sticks to the phosphorus and joins up with the phosphorus, making it heavier. And although they didn't know at the time, it was making something called phosphorus oxide, which is what we know today as a compound when you have 2 elements joined together. So that was why the phosphorus was getting heavier, because extra oxygen atoms were coming to be stuck on to the phosphorus. I hope that makes sense. So it was going from 10 grams up to 11 grams, and at the same time, the oxygen gas was getting lighter. It was going from 4 grams down to 3 grams. Why was the oxygen gas getting lighter? So if I just compare here, that's at the beginning, that's before the experiment. Duck my head out of the way a little bit. And why was the oxygen gas going from 4 grams to 3 grams, guys? They measured the oxygen gas afterwards, and there wasn't as much oxygen gas, only 3 grams left. What was the reason for that, everybody? So this is it before. Oxygen gas before weighs 4 grams. Oxygen gas afterwards only weighs 3 grams. So the oxygen gas has got lighter, only 3 grams now, and the phosphorus has got heavier. It's up to 11 grams. So the reason why, if you're not sure, the reason why the oxygen gas has got lighter, gone down to 3 grams, is because some of the oxygen isn't there anymore. One of them, Emily, that's right, well done. One of them has gone in and left this box and has gone and joined up with the phosphorus. Okay, And before Lavoisier worked out how to measure the weight of gases, nobody had ever seen that the oxygen gas was getting lighter and the phosphorus was getting heavier. So Lavoisier thought, okay, something from the air is going to join up with the phosphorus, and that's where the extra mass is coming from. Really good, Emily. Well done. Well done. All right, so this led Lavoisier to come up with like a big idea. And basically, he said that if you have a chemical reaction, if you weigh the things at the beginning, everything you have to start with, that's called the reactants. Now, in this case, it was 10 grams of phosphorus reacting with one of these oxygen gas atoms, which were 1 gram each. So 10 grams of phosphorus plus 1 gram of oxygen. They should, because you never destroy atoms, you never create new atoms, you don't just magic new things out of nowhere. If you find how many grams of phosphorus and how many grams of oxygen you have at the beginning, it should be the same as the products, what you have at the end. Okay, so if you have a look at this at the beginning, 10 plus 1 adds up to 11, and then the phosphorus oxide at the end adds up to 11 as well. So his idea was, okay, things get heavier when you burn them, some things like phosphorus, but that extra weight isn't just being magicked out of nowhere. That extra 1 gram, so where did this extra 1 gram come from? The extra 1 gram has come from some oxygen gas that was already there. Okay, so this rule here, the mass of the reactants is your ingredients before the reaction, product is the things that you have at the end of the reaction. This rule came to be known as, slightly in the way, this was known as the law of conservation of mass. Mass is when you measure something in grams, and conservation means it is kept the same, it stays the same. So conserving mass means that the mass is the same at the beginning and at the end. Well, Jesse, that's good news, because we only have 3 or 4 minutes left of our lesson, so then you can go and enjoy it. So, all right, so that was this idea that things in a chemical reaction, the things at the beginning and the things at the end always weigh the same amount of grams, was Lavoisier's massive idea, and it sort of changed the way that people looked at chemistry. Because remember, before Lavoisier's idea, if we just go back to the alchemists, people thought that there was something called fire, and it could be removed from chemicals and things could get lighter or heavier. But actually, Lavoisier had shown that things can't just get lighter or get heavier. It has to have extra atoms added onto it. All right, and then, so this is his idea. This is like the key thing from today's lesson, the law of conservation of mass. And then the last thing I want to show you is, what about charcoal? So how does Lavoisier's idea explain what happened to charcoal? Can you remember what happened to charcoal? Did it get heavier or lighter when you burned it? So we talked about that right at the beginning of the lesson. So if you weren't here right at the beginning, what happened to charcoal, guys, when you burned it? So 16 grams of charcoal, did it get heavier or did it get lighter? It was not the same as phosphorus when you burn phosphorus. So when you burn charcoal, that's right, Josh, it got lighter. Phosphorus, remember, just take back to phosphorus. Phosphorus got heavier because oxygen atoms joined onto the phosphorus, went from 10 to 11. Kirsty, Emily, good stuff, well done. So charcoal, however, got lighter. So how did Lavoisier explain this? Well, what he found was that he measured the gas very carefully. He had some oxygen gas, and by weighing it, he measured it was 3 grams. And he had some charcoal, 16 grams. How many grams is each charcoal atom if this box of charcoal is 16 grams? Idiot Sandwich has joined us. Or perhaps he's been here all the way. Been a bit quiet, Idiot Sandwich. Good to speak up now, though. So how much would one Lucy, that's right, every gram of charcoal, sorry, the C stands for carbon, charcoal is made of carbon. Each one of these must be 4, right? Okay, so that's before burning, 16 grams. And then when you burn the charcoal, this is what happens. One of the carbon atoms goes off, and some of it goes off and joins with oxygen in the air, and that makes something new. That's called carbon dioxide when carbon joins with oxygen. So why has the charcoal got lighter after it's burned? The 16 grams has gone down to 12, and that's because one of these carbon atoms that was in the charcoal has gone into the air. Now, Jessie mentioned that right at the beginning. She said, well, when you burn something, you make smoke, right? And things go into the air, and you weren't far off, Jessie. So you're making carbon dioxide when you burn charcoal, and some of the carbon that's basically in the black charcoal at the beginning ends up going into the air and making carbon dioxide gas. So it's just like last time, something was joining up with oxygen, but this time it's going up into the air. So have any new atoms been created? No. You still have 4 carbon atoms, just one of them is over here, and 3 oxygen atoms. So that's the beginning. That's as it is at the beginning. That's as it is at the end. So no new atoms have been created. Have any of the atoms been destroyed? No. You've still got the same atoms as you did before. So basically, all that's happened is that one of these carbons has gone up into the air, and that means that if you add up the things you had before, 16 plus 3 gives you 19, and if you add up the things you had afterwards, the charcoal's gone down to 12, the gas has gone up to 7, that adds up to 19 as well. So it explains why charcoal got lighter, but the phosphorus got heavier. So people understood chemistry so much better after Lavoisier had done some of these experiments, just because he could measure gases there. And that's the last bit of chemistry for today's lesson. Well done if you followed that through. You can watch it back again, or ping me some questions if you're not sure about that why the charcoal got heavier when it got lighter when it burned, why the phosphorus got heavier. Now, last thing is a little bit of a sad. Are you ready for this? Prepare yourselves for a bit of a sad ending to a lesson. A sad ending. Do you remember what Lavoisier's job was? His wife's dad, it was mentioned in the little video clip, his wife's dad was in the tax collecting business. That's where he had a lot of money from, his father-in-law. Now, a revolution happened, the French Revolution happened at the end of the 1700s, 1790s, and the poor people kind of rose up against the king, and they chopped off the head of the king and took some power for themselves. Poor people had been put down upon in France, and a lot of rich people in France were executed by guillotine. So taken off to the town square, had their heads chopped off. And Antoine Lavoisier, even though he was basically just a scientist, he wasn't too much to do with the rich lifestyle, although I suppose he did know quite a lot of rich people. He was caught up in this, and because people hated tax collectors, his father-in-law was executed, and he was also taken to the town square in Paris and had his head chopped off on May the 8th, 1794. And so it was a bit of a sad ending. He was only, I think he was in his late 30s, early 40s, so not very old for a scientist. He had lots still to do. We've had 2 beheadings, Jessie. I had not even thought of that. We've had 2 beheadings in today's lesson. We've had the jelly baby, which sadly lost its head, and now we've had Antoine Lavoisier, one of the greatest scientists of all time, having his head chopped off. And one fellow scientist wrote afterwards, "It took them only an instant to cut off his head, but 100 years may not be enough." 100 years may not be enough to find another like it. So what he was saying was this was a brain that only comes along every once in a while, a person this smart only comes along. And I've just talked about like a couple of his experiments today, but he just was such a genius. He did a lot for science and chemistry, and a lot of people worked on his ideas following him. And if when I finish this lesson here, when I send you out the slides, guys, there is a link to a little article about Marie-Anne Lavoisier, who was quite an amazing person herself. If she was born today, like I said, she might have had the chance to become a really good scientist, and you can read a little bit more about her story if you just click on this link here. So it's just a little link to a little description of her and her life there. All right, so that's something you can have a look at for yourselves.